Let's get started today's seminar. Today's seminar speaker is Dr. Juri Smirnov, and he will talk about the Co-SIMP miracle. So please start.
Thanks a lot. I'm very happy to be here. First time at CHAOSS, even though virtually. And let's get started. We know that dark matter is a new particle. And we know that because from cosmological measurements, we know that it's not made of ordinary matter. We are convinced that it's not a Mond-like theory in terms of modified gravity, because it acts on so many different length scales, and Mond-like theories so far cannot accommodate for that. We also know that it's not made of light neutrino species, because they wouldn't be abundantly produced in the early universe. So there has to be a new particle in nature, and we can think about ways how to produce it, because that gives us a lot of theoretical control about the models and lets us potentially test them. A very well-known example is the so-called weakly interacting massive particle production mechanism, where we have a particle that freezes out by two dark matter particles annihilating to some standard model particles, for example, electrons or other final state of the standard model particles. And that fixes the annihilation cross-section to a certain value, requiring that the annihilation rate drops below the Hubble rate in the early universe, which fixes the dark matter abundance, gives us a target value for this annihilation cross-section. So if we have stronger interactions, we end up asymptotically. When we evolve in time, the dark matter abundance, we end up with less dark matter. If we have weaker interactions, then we have more dark matter, and the sweet spot is essentially the if the cross-section of the annihilation is of the order of the weak scale interactions. That's why people called it the weakly miracle, or the weakly interacting massive particle freeze-out mechanism. That is a very well-known and well-studied mechanism. And if I may show you this cartoon overview of the search strategy that is motivated by that, is essentially this parameter space of dark matter mass and this dark matter annihilation factor, sigma v. And we know from the production mechanism that we cannot have a production rate that is below a certain threshold value, because we would have too much dark matter in the universe. It would not annihilate away enough. So the rate factor of this annihilation has to be larger than a certain value. There are experiments that are searching for that, and a very large role experiments play that look at annihilation in space, either satellite-bound or Earth-bound experiments that look for signals from the annihilation. And of course, they probe lighter masses because they have a higher number densities first, and also larger rate factors first. So they try to close this parameter space from here. There are also unitarity considerations of the theoretical studies of the cross-section that constrain this parameter space from the other side, and that leaves us with a certain uncharted territory, and experiments are trying to progress and test it. But that's the general approach, and those models are strongly motivated by mediator type models that resemble, let's say, QED. If you have some vector mediator that is connecting the dark particles with the standard model particles, then this topology is very strongly favored, or it is clear that this topology should exist if you have a mediator particle of this type. If it's a vector, a scalar, is a model building question, but there's many ways to UV complete those models. Or on the other hand, from QED type interactions, you're naturally led to this type of interaction topology. However, nature is more rich, as we know from QCD and the low energy interactions of QCD, for example. They are number changing interactions, such as kaon interactions that convert kaons into pions and changing the number of particles that are involved. Those are all mesons, but in the process, the number of mesons changes. it was for a while not really clear what kind of Lagrangians can be written down to describe those theories. And in a very famous paper by Edward Witten, he showed that it is possible to write down those kind of topological theories that describe this interaction process, which is a whole subject by itself. But the point is that it is possible to write down an effective theory, the effective description of the theory, where we have this 3-to-2 interaction that naturally arises from rather fundamental symmetries. So we can also apply this type of ideas to the freeze-out of dark matter. One is suggested by Unit Hofbeck and collaborators, where all the dark sector particles reside in the dark sector. All those particles involved in this interaction are from the dark sector, and we have number changing interactions. So as I showed you before, you can have 2 to 3 meson interactions or 3 to 2. And if we apply this idea to dark matter freeze-out, we can have 3 dark matter particles that go to 2 dark matter particles, which reduces the number of dark matter particles. And if this interaction drops below the Hubble rate at some point, that fixes the relic abundance of dark matter in the same way as the WIMP interaction freezes out the fixes dark matter abundance at freeze-out. This also gives us a certain target value for the rate factor. However, there's also mass dependence because there's another power of number densities of the initial state particles in the rate factor.
Excuse me, may I jump in with a naive question?
Sure.
How do you define a cross-section for this kind of process, for 3 particles meeting?
Oh yeah. I would rather think of it as a interaction rate. So you have this rate factor 3 to 2 times v squared. You can derive this quantity from fundamental interactions and multiply it by the number density squared. So that is the rate. And so you have to see that this, even though I call it or use a terminology which is very similar for a cross section, but it has a different scaling. It has a scaling of 1 over mass to the 5th power, and not as normal cross sections do for 2-to-2 interactions, 1 over mass squared. So that multiplying by number density squared gives you still a rate. But this is fundamentally computable from the Feynman diagram.
Okay, thanks.
Sure. Yeah, this is always like kind of a mind twist because we are used to think in terms of cross section as an area, but it's not an area. It's because it has another dimension of number density. Here is kind of a different object, but it's so yeah. So the easiest thing for me is to think in terms of rates if you do this multiplication by n squared. Good. So again, just comparing rates gives us the same freeze out for the Boltzmann equations if you solve them, and then we are left to a certain condition on this interaction rate factor. This model is very beautiful because it has in principle only one process that determines the dark matter abundance, but it has another small issue, let's say, that if dark matter freezes out by only that interaction, it would overheat. And this is clear because we convert rest mass into kinetic energy of final state particles, and so the dark matter bath becomes hotter and hotter in the freeze-out process. So how this problem was solved in the original papers is by introducing additional interactions that kinetically equilibrate the dark matter particles with the standard model particles. So you need to add an additional piece of information or of model building on top, which is fine. But we were thinking if it's possible to have a model where you have those 2 features combined. And so John Beacon and I were looking at this process that is essentially a hybrid between the SIMP, the freeze out of these 3-to-2 interactions. Oh, and let me just mention that SIMP, the abbreviation stands for strongly interactive massive particle, because these interaction rates are rather strong compared to the rates of the weak scale here. So we were thinking to combine this interaction of number changing processes in the dark sector with an interaction with the standard model particles. So a possibility is to take the interaction of two standard model dark sector particles with one standard model particle that is only participating in the scattering process in the interaction. So the standard model particle is not eaten, but the dark matter particle is eaten up here. So when this interaction freezes out in the universe, we have freeze out condition that tells us again what is the rate for this interaction that is required to have the correct relic abundance. And again, the scaling here is different. It's not a constant with mass, but it scales with the mass because again, we have a different dependence on number densities of the rate factor. Okay, so if we show that as the available parameter space, I showed you the cartoon before, where for the WIMP case, we just have a flat line and we cannot live below that flat line because if the rate was lower than that value, we would have too much dark matter. Same story here, but now the flat line has become a line with slope. So that is exactly the mass dependence. And so below that line, we have too much dark matter. Above, there's not enough. And on that line is exactly the correct amount of dark matter. There's an additional requirement. The dark matter mass has to be below twice the mass of the standard model particle that is participating. Otherwise, we would have the possibility to send one standard model particle to the final state, and we would have just a normal semi-annihilation process where you would have two dark matter particles going to one dark matter particle and two standard model particles. So there is an additional kinematic condition that closes that channel. How would we detect those kind of interactions, or how could we prove that this is really the production mechanism in the universe today? Let us first look at the connections to electrons. And there, a very powerful experiment is Xenon 1 ton. It's the most sensitive experiment that can look for electronic recoils, and they had found this very rare xenon double electron capture decay, and that resulted in a Nature paper in early this year. And we were using initially their data that they were publishing and showing the most sensitive electronic recoil events to constrain the parameter space for the first time. So saying, okay, if we took that interaction of the Co-SIMP in the detector at late times, we would actually see a monoenergetic signal. So due to the kinematics of the dark matter particle beam consumed and giving its mass to the kinetic energy of the final state particles, if you compute the kinematics, the recoils are essentially monoenergetic. And that would give you a peak in this electronic recoil spectrum. So we were using that data to draw the first constraints in our preprint in February. So this is how the data looks. However, Xenon released data a little bit later in the summer this year of those low energy bins that they were not yet published in February, and that got us very excited because they were actually seeing a certain excess or events that they couldn't really explain by their modeling, and in fact that rate was roughly corresponding to the rate you would expect from the early universe if the mass of the particle was in the ballpark of 50 keV, which then sits right at the edge of the exclusion plot, of course, because that's the sensitivity of the material. We also took the effects of the electron orbitals into account, so that's why the fitted spectrum is not an ideal line, but it actually is more has a certain spread due to interaction with different shells of the xenon atom here. And that is just an energetic energy conservation calculation. Right. So another thing which is interesting about that is the what I call the look right here effect, as opposed to the look elsewhere effect. Namely that if we have the xenon 1-ton experiment and we know its exposure time and mass, and we know that it has observed 50 events, more in this than it can explain by its modeling, then by taking into account the rate factor that we computed from the early universe that is needed for the freeze-out and its connection to the mass, we are led to a certain mass range, which is 30 to 50 keV, and given the kinematics of this process, we know that the recoils have to sit in the bins between 2 and 6 keV. So this energy range, given the rate that the detector measures, is not arbitrary, but is linked. So that's why if we know that we have a certain amount of excess events, we have to live in this energy range. So that's at least adds statistical significance to the analysis. That also motivated us to do further work, and that's why we are looking with John Beacom, Aditya Pari, Klinda, Xu, and Beiju into UV completions of these models, because as you see, these interactions are effective interactions, and we are looking at ways to UV complete those models right now with those people. So that's we are personally also very much motivated and excited by the results from the xenon 1-ton experiment. Well, another way of looking for this type of models is to construct experiments with lower energy thresholds. As I showed you, the parameter space of the models is in the sub-GeV regime, and in this regime is quite difficult to tackle by usual direct detection experiments, because in the elastic interaction, at least, the deposited energy is pretty low. But there are several good ideas on the market how to construct detectors which would be sensitive to lower energy thresholds, like superfluid helium, new materials with certain lattice defects, or superconductors, or even new 3D materials, Dirac materials, which have small energy gaps. All of those materials have small energy gaps that will be sensitive to this new elastic interactions. Those are present in the Co-SIMP model, because on the loop level, on the two-loop level, if you combine this in the effective theory, you're necessarily led to elastic interactions, and the energy is around the EV scale if you are living we have sub-GeV dark matter. So here we estimated the sensitivity of possible or proposed experiments that are proposed in literature, like Dirac materials or superconductors, and that plot shows that quite modest sized experiments with about a kilogram a year exposure could test a large fraction of the parameter space once operational. So that is an interesting way forward, and then we also look really forward to see how the construction of those experiments would go ahead.
Excuse me?
Sure.
Excuse me? So in this slide, so do you assuming that the thermal rally condition is achieved by the top diagram, 3 to 2 scattering, and the direct detection at xenon 1-ton is realized by the second middle diagram?
Okay, the direct detection is by of the elastic process here.
Yeah.
Is realized by this diagram, but xenon 1-ton would not see that, because in this mass range, the energy deposit is too small for the xenon 1-ton detector. So so the limits, the gray limits here, are from the xenon 1-ton experiments, and they also come from the first diagram.
Okay,
but,
I see.
Right. Okay. So there's dotted lines of experiments with a sensitivity to lower threshold energies. They would move further in the parameter space, because they have the rates of those processes are higher, because they have only one particle of dark matter in the initial state. But it's a challenge to measure those low recoil energies. Okay. So I want to briefly mention also the possibility that you could nucleophilic co-SIMPs, of course. You could have the same process, but that couples to protons or neutrons or other nucleons. And here the situation is in principle similar, with the same type of slope for the prediction for the relic abundance. But since we are in a larger mass range, or we can live up with masses that are significantly larger, going to the GeV scale, the flux or the rate of the interaction in the xenon 1 ton detector of this process is weaker, and it does not really touch the relic abundance line yet. But the loop-induced processes are again promising, and there are some experiments which already touch essentially the relic abundance line. Those are cryogenic calorimeters that sit over ground, because, and they can be sensitive to those elastic interactions because they don't have the overburden of the Earth that would block those particles, dark matter particles, from reaching them at the rather large elastic cross sections. To go lower in mass, some other experimental technique would be needed. And here, for example, the superfluid helium detectors are a very good option that are sensitive to those low energy depositions for processes that scatter off nuclei. The other constraining thing here is also dark matter self-interactions that we estimated from another two-loop diagram, and that is limiting the parameter space in the very low mass region. There is like another search that I wanted to present, which we recently discussed with my collaborator Rebecca Lee, and that is connected to the Co-SIMP process, because it allows us to thermalize dark matter in a different way after it is captured in celestial objects. You know that dark matter can in principle elastically scatter and be captured in Earth or in any star or object in our universe. However, in order to have efficient heating of those objects that could be a potential signal, you have to reach annihilation equilibrium. The capture rate has to equilibrate with the rate at which dark matter, after it has sunk to the core, self-annihilates and deposits its mass energy into the heat of the object. For normal 2-to-2 annihilations of dark matter particles, that gives us a certain condition on the annihilation rate that has to be larger than a certain value. The problem is with light dark matter that those annihilation rates are already excluded by direct detection, indirect detection in satellite experiments that look for those processes in space for smaller masses. So for masses below the GeV, the equilibration is very challenging because already indirect detection experiments exclude those type of larger rates. The situation is different if we have these Co-SIMP processes because they are more difficult to see in indirect detection experiments, but they can bring dark matter into equilibrium in terms of releasing mass energy into kinetic energy in the planet, if those particles are gravitationally captured by elastic scattering. So that brings us to this new opportunity to study light dark matter that is captured in planets. And John Beacom already in 2007 had a paper, and they looked at the constraints from the Earth heating and the heat flow from Earth and how it can constrain the dark matter parameter space. But those constraints cut off around the GeV scale or even at few GeV, because dark matter can evaporate again from the Earth, because the temperature in the Earth core is such that sub-GeV dark matter would have thermal velocities that are above the escape velocity of our planet and would just leave it again. So we're thinking to look at different objects in space, and there are many different objects that you could look at. For example, neutron stars, they have great gravitational potentials, but in order to see them cooled or heated, you need to find very cool neutron stars. And those are very hard to see because they're so small. There are also white dwarfs that are easier to find, but they have significant heating on from their processes in their cores, and they have a very strong background essentially. So you would have to have a very sensitive understanding of the cooling models and all the heat distribution and modeling and understanding of the star in order to set any constraint. There are of course black holes that are interesting for other purposes, like their change of their spin if they interact with light dark matter. But for our study, unfortunately, it's useless because we cannot really measure the temperature of a black hole. So what we are left with are really big giant planets and substellar objects that have much less heating background, and those are called the brown dwarfs. So they are essentially up to 60 or 75 Jupiter masses, heavy, before they're really massive enough to start burning nuclear elements efficiently and heat up too much and become so-called M dwarfs. So those brown dwarfs and Jupiters and super Jupiters are very good targets because they have low heating backgrounds, but still they have strong gravitational potential that allow to capture light dark matter, and it would not evaporate since the escape velocities are much larger than the escape velocity from Earth. So looking at different types of planets that we can study, we have of course also rocky Earth-like planets that are exoplanets that we could look at, and there are many of them, but it's unlikely that we could understand the features of those planets better than our own Earth. So probably the best limits we have from Earth, the best limits from those type of planets are the limits we have from our planet. So that's why it's good to focus on those Jovian and brown dwarf planets. And what I also want to mention, they can go rogue. So rogue means that they are escaped from their host star and flying somewhere lonely through space. And that is a very good opportunity for this type of search because they have essentially zero heating from their parent star because they have none. And they are also, it's also possible to see them quite far away towards the galactic center because they're not outshone by the parent star sitting next to them. So we can really measure their temperature independently of the parent star quite far away from our planet. And that opens up a very interesting possibility, which I show you in a moment. But the flagship experiment that can really test those type of objects is the James Webb Space Telescope. We were looking at the sensitivity of this experiment to the measurements that we want to perform. And it has a very large mirror mounted on top and two different instruments, one near-infrared imager that is good for temperatures above 500 Kelvin of the exoplanets, and another mid-infrared instrument that is good for temperatures between 100 and 500 Kelvin of the exoplanets. So it can see really rather cool objects. It's supposed to start to launch in autumn next year. Hopefully it will happen. And the interesting possibility I was telling you about is to see a change of the planet temperatures if you go towards the galactic center, especially because you can measure their temperature independent from their host star. And if you look closer and closer to the galactic center, we know that the dark matter density in the galactic center significantly rises. So instead of this kind of magenta case where there's no dark matter heating, we can hope to see a rising temperature of exoplanets when we move closer to the galactic center. This radial rise is not expected in any astrophysical model at those distances from the galactic center and would be a clear indication of a dark matter heated exoplanet population. We show here in this paper the this blue line shows the sensitivity of the James Webb Telescope. So the temperatures above those lines could be seen by JWST. It also shows that if there was dark matter heating, the James Webb Space Telescope would find significantly more exoplanets at large distances from us than we naively expect. So there are different studies possible, especially having large statistics, and there's hope to really measure tens of thousands of exoplanets with the James Webb Telescope. So having these large statistics would hopefully give us more control and the new possibility to search for those dark matter-induced signals. In terms of parameter space, I can show you that the Jupiters and brown dwarfs have better sensitivity to low mass dark matter, exactly because of this enhanced gravitational potentials and the possibility to not let it evaporate. So we move from around the GeV region to significantly sub-GeV masses up down to around a few MeV masses, actually, for the heavier brown dwarfs. Here in this plot, the sensitivity to the elastic spin independent cross-section is shown, and which is necessary for the capture. And here we showed two benchmark values, one cross-sections, one line which shows that at cross-sections above that line, all the dark matter that passes through this brown dwarf is captured. And there's this dotted line shows the benchmark value where only 10% of the passing through dark matter is captured. And this, of course, is much more difficult to measure, but with enough experimental sensitivity and statistics, we hope that this 10% benchmark value could also be reached. And that shows that essentially this quite widely open parameter space of low mass and rather intermediate spin independent cross sections could be probed with those new approaches to dark matter. So finally, as I said, as I told you before, the theory we have written down for the Co-SIMP is still an effective theory, and we would like to understand better its properties by UV completing it. We have several models, essentially also based on a vector and a scalar mediator that can have different interaction topologies to UV complete that model. And we hope that we can study processes at high energy that, of course, in the EFT are not accessible. So, for example, we can imagine that if you have those number changing interactions of a particle in an accelerator experiment where you produce the Co-SIMP at large energies and interacts with a standard model particle, those number changing interactions would lead to those type of showers where you grow the number of standard model and dark sector particles. And depending on the properties of those particles in terms of lifetimes, the spread of this shower can be quite large. So you could have a much fluffier shower essentially than you would have normally expect from the electromagnetic interactions. So there's an interesting possibility to play with those UV complete models. We also would like to assess the process of stellar cooling and understand it better in UV complete models, because in our simple study of the effective processes, we showed that these rather strong interactions lead to trapping of dark matter inside of supernova, for example. But it would be very interesting to validate and check those estimates in the UV complete model. Of course, it will be also good to compute the loop coefficients in the UV complete models, not just in this connecting effective operators. And finally, it is extremely interesting to look at the early universe thermalization, how these models with large degrees of freedom affect the number of relativistic degrees of freedom. When do they actually thermalize? Because those questions are really depending on the UV completion and the mediator properties of those models. So in summary, I wanted to say that we have found a new way to produce dark matter thermally that is quite predictive. This process can be directly tested in the lab, and maybe if the xenon experiment really has seen an access, it could in principle be explained by a Co-SIMP type process. And finally, there are induced processes such as these elastic interactions that are happening at loop level that can be tested in other laboratory experiments. And also it allows us to go further and have a new astrophysical searches as the planet heating search for light dark matter. So with this, I would like to conclude and thank you again for the invitation. And yeah, do you have any questions?
Okay, so I have a question. So in the general Co-SIMP scenario, you expect that the dark matter mass is sub GeV in
Yes.
general, and the later part of your talk is about generic SIMP Co-SIMP scenario, not only for the general lantern access, right?
Yes, exactly.
Okay. So and for the general lantern access, you assume no, for the leptophilic Co-SIMP scenario, you assume dark matter mass is below twice of the m electron mass of electron.
Yes.
And then for such a very light dark matter, there may be some constraint from CMB, or do you, for example, do you prefer scalar or fermion dark matter in that case? And also, do you discuss any other constraint on such a light dark matter?
Yes. I mean, yes, there's, you're right. That's a very good question that we discussed in this effective framework in the original paper. And we're also thinking about that right now with my collaborators in the UV complete framework. So
I see.
To answer that, I would say is they're different things. So one question is to ask, when do those models thermalize? And in principle, what we are finding is if we have those quite light masses and they have a mediating particle that is connecting the dark sector interaction and the visible sector interaction, the process that is most efficient at thermalizing this dark sector is the decay and inverse decay of this mediator. And in principle, you can have a model where the inverse decay and decay of the mediator thermalizes the particles at below the BBN temperatures. So that avoids the issue or the constraint from the having additional relativistic degrees of freedom at BBN. And then you have to think about the number of relativistic degrees of freedom at CMB.
Right.
But now we have a particle that kind of, so there's a canceling effect. We have relativistic particles that are coming in the equilibrium and leaving it again. At the same time, they're enlarging the electron bath from which then energy can be drawn. So there is, if you go through the calculations of this entropy conserving sectors, you will find that there's an interplay of effects. So you have first the growing of number of degrees of freedom, and then it drops again actually below 3. So you have a negative contribution to delta N effective at CMB. So having the right amount of degrees of freedom allows you in principle also to have at CMB the right amount of degrees of freedom that is constrained by the CMB observations. So there's, at late times, there's an interplay and cancellation effect that gives you delta N effective in agreement with 3. But it's a quite non-trivial mechanics, I must say. It's quite interesting.
And for the nucleon philic scenario, what is the favored range of the dark matter mass in that case?
That will be around the hundreds of MeV or the GeV scale.
Okay.
So below twice the proton mass. Yeah.
So typical SIMP scenario case. I see.
In terms of mass,
Yeah,
yes.
Yeah,
Mhm.
yeah.
Exactly.
So when do you expect to finish your work on the UV completion for the leptophilic Co-SIMP scenario?
Yeah, I mean, we are actually quite progressed. I mean, those
Okay.
questions, so, you know, I would say maybe by the end of the year.
Okay.
But
I see.
you know, like all my collaborators, not all of them, but most of them go through application processes in the meantime. So
Right.
you know that it's possible to have a certain delay there. But yeah, I hope that within like 4 weeks we should be done.
Okay. Looking forward to see your new papers.
Thanks, Professor Ko.
Okay, other question? Okay. I think there is no more question. Okay. Then let's thank